All right, today we are talking about the atom. This is going to be a really short, sweet lesson on the atom. But the first thing we've got to do is fill in the review up at the top. So just like always, you've got that little quick review at the top of the notes that reviews the last set of notes. So you've got your word bank right here that you're going to use to fill that in. And here we go. Dalton had his marbles. Thomson had his muffins. Rutherford saw empty space. Bohr had his rings. How boring. And Schrödinger made it 3D. So this is to help us remember that Dalton thought that the atom looked like a marble, a small solid sphere. Thomson thought that the atom was more like a blueberry muffin, a perfectly round one, where the cake part was the muffin part and the blueberries were the electrons scattered throughout. The cake had a positive charge and the electrons were negatively charged. Rutherford said it was mostly empty space, and he was right that really the atom is mostly empty space and that the nucleus inside is very dense and condensed. Bohr said that all of the electrons traveled in rings, and he was right about there being energy levels, but they aren't in these perfectly concentric rings like he had, because we know that Schrödinger told us, nope, that whole atom is three-dimensional. It's not a fried egg. It's round and 3D. All right, so what do we know about the atom? A single atom is very, very, very small. If we think back to the video that we watched, just how small is an atom, if we took a grapefruit and we blew up all of the atoms in that grapefruit to the size of blueberries, so that each atom was the size of a blueberry, that grapefruit would now be the size of the entire Earth. In the center of the atom is the nucleus. And a student has popped in for some help, so I'll be right back. Okay, so in the center of the atom is the nucleus. It contains the protons and neutrons. Protons have a positive charge. So the way to remember that one, I know most of you probably already do anyway from the 6th grade, but the way to remember that one, you think of yourself as Sylvester the cat. You remember Sylvester's a cat, like Tweety, Sylvester, right? So protons have a positive charge. Protons are positive. I know, it's silly, but I've said it a million times. The sillier it is, the better it sticks in your head. So protons are positive. Now, this is the one that, every year somebody, half the class comes in telling me that neutrons are negative. They're not. Neutrons are neutral. They have no charge. They are neutral. So neutrons have no charge and are neutral. So our silly little mnemonics to remember: protons are positive, neutrons are neutral. The nucleus is very, very, very wicked, stupid small. Like as many adjectives as you can fit in for describing how small something can be. This means that it is very dense for its size. So it is very small, but it's heavy for its size. Like it's so tiny, we can't even wrap our heads around it. And yet it's got an amazing amount of density in that size. So most of the mass of the atom is in the nucleus. The area outside of the nucleus is called the electron cloud. It contains electrons, magnetic fields, and empty space. So really electrons and empty space are what you need to know. Electrons have a negative charge. So back to our mnemonic, protons are positive, neutrons are neutral, and electrons are so negative, oh my God. Okay, one more time. Protons are positive, neutrons are neutral, and electrons are so negative. Hair flip, right? Got it? Oh, wrong side. Hair flip. So negative, up. Okay. Electrons travel around the nucleus in orbits. As they gain or lose energy, they move up or down in those energy levels, in those orbits. All right, so the last thing we've got to do for these notes, like I said, they're pretty short and sweet, is to draw an atom. Now, realize that there's a couple of things. Number one, we cannot accurately draw an atom because to be able to represent how small the nucleus is to how large the empty space of the rest of the atom is, I can't possibly show that on paper. So realize this is not to scale. Our nucleus is going to be much, much bigger than it really should be, even considering if our whole atom was the size of this square on the paper. If the whole atom was this size, we still would not be able to see the nucleus. So we are drawing so we can learn, so just know that it's not to scale. The other thing you need to know is that we're going to draw sort of the Bohr model of the atom. And remember that Bohr's model is not accurate, but we like using it because it's easier to learn from. When we look at Schrodinger's model, the modern model, the three-dimensional model, yeah, sure, that's much more accurate, but how do you tell where anything is? It's impossible. So we use Bohr's model to help us out just for learning. All right, so normally this is where I would draw a name from the cup and someone in the room would pick one of the atoms somewhere between 1 and 10. So either hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, or neon. I happen to have someone in the room. You're willing to pick something? Okay, I will. How about carbon? So carbon is number 6. It's the letter C, carbon. So we're going to label our top with carbon, C. And then we're also going to label it with a 6 because we know that that's its atomic number. And then we're also going to label it with a 12 because that's its atomic mass. And we're going to need those two numbers to be able to draw our model here. So the first thing we need to do is draw our nucleus. So we know it is a carbon atom, so it has 6 protons. So we need 1, 2, 3, 4, 5, 6 protons. Now notice I kind of spread them out a little bit. That's because we've also got to put the neutrons in there. And so we put some space for us to fit in the neutrons. Okay, now we know that it has a mass of 12. So that means that it also has 6 neutrons. How do I know that? Because 6 plus 6 equals 12. So the number of protons plus the number of neutrons equals the atomic mass. We'll talk more about that as we go. But it's basically a really simple algebra problem. You know what the answer is, the total, the atomic mass. You know what the number is of the number of protons, so you've just got to solve for x. You've just got to find out what plus the number of protons equals the atomic mass. So 6 plus 6 equals 12, so we know we need 6 neutrons. Now, I'm not going to put any kind of a plus sign or a minus sign or anything in that. Why? Well, because they are neutral. So the protons are positive and the neutrons are neutral. So we need to label one of our protons as being a proton. I'm trying to label it as being positive. I don't want to do that. It is positive, but that's not what I was trying to label. And we want to label our neutron. And then that whole thing is the nucleus. Oh. It was supposed to be green, but it didn't happen. All right, and that whole thing is the nucleus. All right, so now we need our electrons. Typically, in a stable atom, it has the same number of electrons as it has neutrons. Otherwise, it becomes an ion. It has a charge because it has more protons than than electrons, or it has more electrons than protons, and it becomes a negative ion. But if this is a standard neutral atom, not an ion, it's going to have 6 electrons. So we need to put in those 6 electrons in these energy levels outside. So we're going to put in 1, 2 on the first energy level. And then 3, 4, 5, and 6 all go on the second energy level. And then I'm going to try one more time with changing the color. well, maybe if I do this. Yep, okay. And that's an electron. That's not worth it. Ain't technology great when it works? And then this whole thing is the electron cloud. So you have the electron cloud with the electrons in empty space, and the electrons are arranged in these energy levels. Then you have the nucleus with the protons and the neutrons. Protons are positive, neutrons are neutral, and electrons are so negative.